second quiz. November 16. And topics will be whatever we are covering from the last quiz from today's lecture. So covering from the last quiz, after the quiz, right? From the material after the first quiz to today. So whatever I'll be teaching today could be very important, right? So I would put the emphasis on today. So today's class will cover about 50% of the quiz. And whatever material that I have covered since the last quiz will be 50. It's going to be like a 2-hour quiz. So you can prepare 2 pages. Cheating sheet. A4 size. Or if you don't have A4 paper, US letter is okay. Either one is okay. A4 or US letter size. Yes. 8 1/2 inch times 11 inch. So far we have covered 2 very important theorems about the complex integration. One is Cauchy's integral theorem that covers that. I think I have to do something setting. I think I have to put the camera off. See if inside of C, then dz is equal to 0. That was Cauchy integral theorem, right? I think I have to set something. Record. Okay, whatever. And second theorem is Cauchy's integral formula. That is, we also covered that. Inside of C, then FC naught. This is actually the extension of the result that I covered. This actually came from this. Z minus C naught over dz over C was 2 pi I. Did I cover that last time? And from this, so that is Cauchy's integral formula. And also we have covered that if we expand using this, if Fz is expanded at let me see. A2, Z minus C0, blah, 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 blah. Then what happens if you integrate? If the curve contains C, if Z naught, if we integrate this counterclockwise, what happens? We have seen that the previous class that all the different order terms vanishes except this one, right? So this becomes as 2 pi I times P1. And this term has a particular name called the residue. And we say Fc has a pole of order n. And this series expansion is called the Laurent series. So the beauty of complex integration is that no matter how the function is complex, you only need to worry about b minus 1 term. All the rest, if you integrate, just vanishes. And calculating b minus 1 is actually easy. So this is order n, pole of order n. So Fg is C minus C naught over Pn. N minus 1 n minus 2 blah 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 p minus 1 z minus c naught plus a0 plus a1 z minus c naught blah blah blah. So z minus c naught to the n fc if we multiply by c minus c naught to the n, so we say a to the x is a x is, so we say a to the x. So when I say a to the x means x is a subscript, the power. What happens? If we multiply both sides by z minus c naught to the n and take the limit of z go to z naught, then of course it's bn, right? It's finite. However, n minus 1 fc then because of the first term, it diverges, right? It goes to infinite, etc., etc. So this term is non-zero. So in this case, we know that if we multiply by z minus c naught to the n, and take the limit, then the whole function is finite. But if you take the lower power of z minus c1, like n minus 1, and it diverges, then we say the highest number of power is the order of pole. So in this case, we say Fc has a pole of order n. And in that case, how do we find p minus 1? So let's continue. Z minus c to the n ft is Pn. Z minus c naught Pn minus 1. C minus c naught n minus 1 to the p minus 1, right? Plus c minus c naught to the n a0 blah blah blah. So if we differentiate n minus 1 times, and take the limit, what happens? Oh, we have a mosquito. So if you multiply by z minus c naught to the n everywhere, and take the derivative n minus 1 times, and take the limit of z goes to z naught, what happens? If you take the differentiate n minus 1 times, everything goes 0 until this one, right? And the higher terms. Then obviously n minus 1 factorial p minus 1. And the rest, on the higher the terms are all 0 when you substitute z minus c equal to z naught. So only one term survives. So pole at z equals z naught with an order n, then p minus 1. N minus 1 factorial and dz d n minus 1 c minus c naught to the square fc c to the z naught. And it has a special name called residue. And sometimes we just write by this. So this particular term is called the residue, and denoted by this notation, RES times C naught. So maybe you can take some example. Let me take one particular example. What example do I have? So let's take an example. By this formula, this differential formula, the result of the residue calculated from this differential calculation is the same as the one that FC the question number 1. How many poles? Okay, first question is FT analytic everywhere. The first question is whether FC is analytic everywhere. Yes or no? That could be a quiz problem. Not everywhere, right? Answer. FC has pole. How many poles does it have? 2, right? Z equal 1 and Z equal -2, right? So it does have 2 poles. What are the order those poles? Z equal 1 has order 2, correct. Z equal -2, order 1. Great. So we can actually calculate that. That is easy. Just one. You just multiply 1, right? So residue, you take the limit, -2, multiply by Z plus 2, FC. And of course, divide by 1 factorial, n minus 1, 0 factorial. 0 factorial is 1. dz d0 is just, you do nothing, right? You don't take the derivative. So it's simply z goes to -2, z minus 1 to square over 1 is 1 over 9, right? On the other hand, maybe I'm going a little bit too fast. The residue at 4 equal to -2, z equal -2 is 1 over 9. So the residue, the calculated FC at z equal to 1, residue 1 is you take the limit goes to 1 and 2 minus 1 factorial dz z plus 2 1, right? So it becomes z goes to 1 minus z plus 2 square over 1 minus 1 over 9. And actually, you can do this very brutal way. Just for the sake of fun, by calculating the residue, the residue at pole equal to 1 is minus 1 over 9. And just obtained, let's try to do the other way. Assuming that you don't know how to differentiate. Okay? Still you can do that. So you can just expansion by partial fraction. A1, B1, B2, A0 plus C plus 2, A1. You can just do it by partial fraction, right? And this is the residue. And this is residue, right? So assuming that you do not know how to differentiate, you just using the expansion by partial fraction. This is called how do you say in Korean? Let me see. 부분 분수분해? What about the term? Raise your hand. Partial fraction? Expansion by partial fraction. If you heard about this, raise your hand, please. You didn't learn in high school? Middle school? Probably in middle school, right? High school, middle school, whatever. So we just put it back. Then the first term is you just have Z plus 2, B2, let's say just for the sake of the order, let's just change this to 1. I think that goes well better. So this B2, B1, Z minus 1, Z plus 2, A0, Z minus 1 square, Z plus 2, A1, Z minus 1 square, B2, Z plus 2, B1 Z square plus Z minus 2 A0 Z square minus 2Z plus 1 Z plus 2 A1 Z square minus 2Z plus 1. So you just need to have patience to go through this. P1 Z square plus Z minus 2 plus A0 Z cube minus 2Z square plus 2Z 2Z square minus 4Z plus 2 A1 Z square minus 2Z plus 1. So these two cancels each other. And that gives the obvious answer. There is no Z to the 3 terms, right? There is no Z to the cube terms. And we know that the denominator is 1. So we know one obvious answer. A0 should be? There is no other G3 terms here. So one obvious answer is A0 is 0, right? So that's obvious answer. Very easy. A0 should be 0. Next higher term is G square, right? So let's put some block here. Z square term. Z square term is B1 and A1, right? It should be 0. A1 plus B1. So that means A1 is minus B1. How about Z term? So we have B2, B1, and A1, right? So Z term, what happens? I don't know what happens. P2. Oh. Is there any way that I can change the thickness? Stroke fill. Stroke. Something is very strange. P2. P1. 2. A1. It becomes very thick. I don't know what happens. I'll try to figure it out during the break. And and one final P2, 2B2, 2B2 minus 2B1 plus A1 is equal to 1. So we know A1 is minus B1. Then P2, A1 is minus B1, so P2, 3B1 is equal to 0. So P2 is minus 3B1. Right? 2B2. 2B2, so 2B2 is minus 6B1 minus 2B1 minus B1 is equal to 1. Thus, B1 is minus 1 over 9. P2 is 1 over 9. Right? So actually, we have the same answer, that using more elementary but still working partial fraction expansion. So perhaps you can take a break for maybe a few minutes, and I'll try to fix the problem with the thickness of the pan. To control the thickness of the pan. So maybe too thin. Residue, too thick, right? About this. There are cases it's very difficult to check the order of the pore. For example, 1 over sine z. Question number 1. Analytic. Actually, the question, I posed the wrong question. The right question would be whether this function is analytic everywhere. Answer? No, right? Not everywhere. Question 2. Order of the pore. Oh, maybe I can ask, where are the locations of the pore? Z is equal to, obvious answer is Z is equal to 0, right? Is it the only pore? Plus pi. minus pi plus minus 2 pi 3 pi. So how many poles does it have? Infinite. Sometimes pole is called singularity. So I prefer to use pole, but some books treat it as hold it as a singularity. So basically it's the same thing, but slightly different. So we found the location. Question number 3. Order of the pole. So we have to see that. Try with the simplest one, right? And so let's try with a simple case. Simplest case. N equal to 1. Whether it does have a pole of order 1. That's a question that I'm going to ask, right? So if whether this 1 over sine z, we know that it does have a singularity or pole at z is equal to 0, right? Because when z is equal to 0, sine z becomes 0, and 1 divided by 0 is infinite. The question is whether it is a simple pole of order 1. So what do? We try to check, right? If we like to check this, whether this is finite or not. But we have a little trouble because when z goes to 0, right? But sine z also goes to 0. So that means nominator and denominator are all going to 0. So it's basically 0 divided by 0 term form. And whether we can define the ratio between 0 divided by 0. That's normally it's very difficult to do. So we'll take a detour. When two different functions f of z and g of z becomes 0 when we take the limit of z approaches c naught, then oops. You can take this the following way. Delta goes to 0. Right? using this. So originally, we need to calculate this limit when z is approaching z naught. What happens? The ratio between fc by gz. But you can write down this limit in this way, assuming that z is z naught plus delta. Then this limit is z approaches z naught, same as delta goes to 0 with this, right? And of course, we know that was g is 0 and f0 is 0. So we just subtracted 0, so this doesn't change anything. But we can do this thing. We divide the denominator by delta, and also we divide by the denominator by delta and denominator by delta. It's still the same, right? Because we multiply by 1 over delta and divide by 1 over delta. It's basically just multiply by 1. So we haven't done anything. But it turns out that, what is this? This is f prime z naught. This one, right? So when both numerator and denominator goes to 0 as you take the limit of z approaching z naught, then this ratio becomes just the ratio between the derivative at z naught. This is called the L'Hopital's rule. It does have theorem. L'Hopital의 법칙? Probably you have heard about that, right? In high school or in freshman? High school. Probably just memorized. But you can just show it by 3 lines. Very simple. So we can apply this L'Hopital theorem to 1 over sine z. So residues C, and using L'Hopital's theorem, it becomes just 1 cosine z, right? So this is and it simply is 1, right? How about pi? Pi z goes to pi, z minus pi, sine z, still the same, 1 cosine pi minus 1. So if this function has a pole of order, still 1, right? So fz has a pole of order 1 at c equal to 0, plus minus pi, plus minus 2 pi, etc., etc. But the residue will depend on whether it is even or odd. So 1 or minus 1, depending on whether the location of the pole is 0, 2 pi, minus it is if the location of the pole is even multiple of 2 pi, the residue is 1. On the other hand, if it is odd multiple of pi, minus 1. Another case, another interest is FC 2z plus 1. That is one big difference between the real function and the complex function. Fx e to the x plus 1. This function is analytic everywhere, right? Because e to the x is never 0, never negative. This function is analytic everywhere. Of course, on x. Fz. Same question. Answer. Everywhere or not everywhere. Maybe let's see if democracy works. Everywhere, raise your hand. Okay, about half. Not everywhere. 1, 2, and 3. And undecided, the rest, right? Let me check. What is the value of pi I? Cosine pi plus I sine pi is minus 1, right? So not everywhere. Location of the pole plus minus pi I plus minus 3 pi I plus minus 5 pi I, etc., etc. So odd number, odd multiple, odd integer multiple of pi times I is the location of the pole. So we determine the location of the pole. So what is the order? So let's check. So this limit is also the same as the previous one because denominator and denominator. Denominator goes to 0 when z becomes pi I. Denominator becomes 0 when z becomes pi I. So we can apply L'Hopital's theorem, right? Because both the denominator and denominator is going to 0 at the particular limit. So it becomes 1 over exponential pi I is minus 1. That's the residue, minus 1. Very interesting, right? And differentiable everywhere. So analytic means both continuous and differentiable everywhere. But this function is continuous and differentiable everywhere except when z becomes pi I, right? So it does have a simple pole. Yes?
When you mean analytic, you mean continuous everywhere?
Continuous. So the simplest case is just using, we can either differentiate over the simple pole, so poles at C2, right? So residue C1 is simply Z minus C2 over 1, C1 minus C2 over 1. 1 over C1 minus C2. Residue C2 is C goes to C2 FC C2 C minus C1 C2 minus C1. So 1 over C2 minus C1. That's the residue. Or you can expand by partial fraction. C1 minus C2, C2 minus C1, right? So C1 minus C2, right? Just put it back. A plus BZ minus AZ2 minus BZ1 is equal to 1 over C minus C1, C minus C2. So A plus B must be 0, right? So B is minus A. Minus A Z2 minus PZ1 is equal to 1. So A Z1 minus Z2 is 1. So A is 1 over C1 minus C2. P must be 1 over C2 minus C1. So that's actually residue. And the answer is we can obtain the residue using either way. So you can use the formula, and or in case of pole of order 1, you can use the expansion by partial fraction. And sometimes we use a notation called the simple pole. Same as pole of order 1. So sometimes some books, some mathematics books, will say simple pole. It says that means pole of order 1. So in case of simple pole, you can either apply the formula or using just expansion by partial fraction. Either way is fine. Sometimes partial fraction is much more easier to do that. Okay. In previous class, I mentioned the invasion of British Navy to the French coast. And it depends on the tidal force. So the British Navy, I mean, the head of the British Navy, Admiral Nelson, I presume, would choose the date with the lowest tidal, lowest height of the tide, because it would be easier to land the marine force to the land, right, to the beach. And that, the tidal force can be calculated using this. So, this integral. Napoleonic War. And this is obvious. How do we obtain this integral? So you know that the tidal force, Newton discovered that the tidal force was originated by the gravitation between Earth and Moon, right? So gravitational force between two different locations can be calculated from the center of the Moon. So it's proportional to here, right? Force. And you need to take the average out from the Moon's surface. So actually, the tidal force integral over 2 pi d theta. Of course, some constant, some gravitational constant in front. 3 times m1 m1 and divided by 4 pi, I think. There's some constant. Because you have to take out all the different, moon is rotating, Earth is rotating, so you have to take into account every of this. And this tidal force just becomes this one. 1 over r1 square, r2 square, minus 2, r1, r2, cosine theta, right? So this integral actually is this form. Cauchy was really, he must be really genius that without even computer, he was able to calculate this force. So let's do this a little bit more elaborate. So this is actually the behind the story of why this integral comes in as an exercise problem for this class. And this actually over 200 and maybe something year old problem. 1789, so it's early, late 18th century. So about maybe 240 years ago, something like that. So, but most of the mathematics books doesn't have this behind the story. But I think if you know the story, that will be more interesting, and maybe have some more motivation to study. I mean, even though you have a much better tool today. So now let's go back to the math. That's actually behind the story. Tidal force.
Tidal force.
Right.
Is it the same formula for electric field intensity?
Exactly.
Oh, okay.
So that's called the inverse square law.
Okay.
So both electromagnetic theory, electric force between two different charges, Q1 and Q2.
So you could assume the Earth and the Moon are two different charges?
In a way, yes.
Okay.
It's always attractive. The gravitation is always attractive. And electric field, if the same charge is the same sign, is repulsive, right? So that's the difference between electric force and the gravitational force. So electric force can be both attractive and repulsive, depending on the charge, the sign of the charges. But in case of the gravitation, it's always attractive. But yes, inverse square law. We apply the same thing. But at Cauchy's time, the electric force was not known. It was before the discovery by Michael Faraday and Maxwell. So 1789, the Augustine Cauchy doesn't know about this electric force. But about 100 years before, Newton discovered formulated the gravitational law. So Cauchy knows about gravitation, and he was able to formulate what would be the force on the tide, the tidal force, depending on the distance between two locations relative to the moon, right? So basically it's the same problem, but in Cauchy's case, it was a gravitational problem. 1 over, so enough of this history, d theta a plus b cosine theta. Maybe assume that a is b greater than b. So Cauchy's first idea is to transform into the complex integration of a circle. Yes.
This is for tidal force intensity, like that?
I mean the previous one. So Cauchy was trying to transform this integral into the complex integration along the unit circle. The step number 1. Cauchy tried to transform the theta integration to the complex integration along the unit circle. Unit circle means circle with radius 1. Unit circle is a circle with radius 1. So this is 1. So you put z as exponential I theta. Then, of course, d theta, exponential I theta, I d theta, right? And this can be I z d theta. So dz is the same as, d theta. Iz over dz. That's the first step. Cosine theta, 1 over 2 exponential I theta, exponential minus I theta, right? So this is same as 1 over 2 z plus 1 over z. So this is step number 2. So that's how Cauchy transform this theta integration into the complex integration over this unit circle. Okay, I will have to draw the pictures. I just saw that today's number of COVID infection is 58,000 today. It was like 18,000 yesterday, but today is 58,000. So about 40,000 more patients positive. Wow. So there was a prediction that the COVID will just go up again. So you have to be really careful. So, okay, so I still haven't figured out how to copy the previous page into the next page. I kept promising you that I will figure it out, but somehow it's very difficult to do that. Maybe I'm getting old. The formula. So let's go back. This is a unit circle. So T theta is Tz over Iz. Cosine theta 1 over 2 z plus 1 over z. So 0 to 2 pi a plus b cosine theta d theta becomes cross integral over c a plus b over 2 c over 1 over z dz over iz. So So it becomes 1 over I AZ over B over 2 Z square plus 1 over DZ, right? So maybe we can put 2 out, 2 over I B Z square plus 2A over B plus 1 over DZ, right? So poles, location of the pole can be 2Z equal to 0. So there's a middle school problem, right? So Z 1, 2 is minus A over B plus minus A over B square minus 1 . So assuming that if A is B is positive and Z1 minus A over B plus Z2 one thing is obvious. When A is greater than B and both are positive, then Z2 must be less than minus 1, right? I mean, if we're assuming that both A and B are positive and particular A is greater than B, then minus A over B is less than minus 1, right? And if you subtract this term, then Z2 must be obviously less than minus 1. So we know that somewhere here, right? So one of the poles is outside of this circle, and only Z1 is inside. So we only need to care about, so this integral actually, this integral becomes simply 2 pi I residue Z1, right? Because we don't have to worry about this Z2, this is already outside of this circle. And we are only concerned with the pole inside of this C. So only one pole. So residue, we already obtained this residue, right? So maybe here. Residue C1 is, let's go back, C1, Z2. C2 is, so this is Z1 minus Z2 is what? 2i over this, A over B square minus 1. So it becomes 2 pi I twice over IB and twice over A over B square minus 1. This I cancels, this cancels, becomes 2 pi A square minus B square. Let me check if my answer is correct. Yes. So that's what Cauchy obtained about 240 years ago. Yes?
Why don't we care about the external pole?
Yeah, because of Cauchy's integral theorem, if we integrate this whole circle, if there is no pole, it's 0, right? If there is one pole, that's 2 pi I times this pole. And we are only concerned with this inside. So if the pole is outside of the circle, it doesn't contribute. You don't have to worry about that.
No, you mean no electric charge, right? Like that? In this case, gravitation.
No,
No?
no. You don't have to worry about that.
Okay.
So this actually Z1, Z2 has nothing to do with the location of the charge.
Okay.
The location of the charge was already implied in the coefficient A and B. The original location of the charge was put into A and B,
Okay.
not this Z1 and Z2,
Okay.
right? Let's just cover one more problem and then maybe stop the class. Actually, I have 3 more problems, but maybe you like the less amount of material to digest for next quiz, right? So this is a very simple integral, just using two simple poles, and actually one of the poles doesn't contribute. And using this very simple technique, Cauchy was able to predict which day the English Navy would land in Normandy. About 240 years ago, so it must be amazing, right? He just only had a pencil and paper. No calculator. So he had to calculate everything by hand using pencil. Another case. So this is the integral that you already know. Probably you might have encountered this integral in your freshman calculus. What is the derivative of arctangent x? We have covered it a few classes ago, right? 1 over x, right? So this is basically tangent inverse x dx. So tangent inverse x infinite and minus infinity. So tangent x is infinite when x is equal to pi over 2. Minus infinite when minus pi over 2. Pi. One of the intriguing things about math is many integrals, which has nothing to do with the circle, seems to give a pi. So pi is like the rate of the circumference between the diameter, right? And for some strange reason, many integrals give pi. So maybe it is embedded in nature. I don't know how. You can treat these different integrals, c squared plus 1. So let's forget about that integral for a moment and consider this function, the same question. Analytic everywhere? Plus minus I. So not analytic everywhere. And z equal plus minus I is the location of the pole, right? So this is z minus I, z plus I. The residue I, C1 minus C2, right? So I, C1 is I, C2 is minus I. So Z1 minus Z2 is I minus I, 1 over 2I. Residue minus I is minus 2I. That's the value of the residue. And we consider the following integral. Sorry. We know the answer, right? If we integrate. Just simply 2 pi I residue I, right? Of course, there is minus I, but it doesn't contribute. So 2 pi I times 2I is pi. We know this answer. But this integral, that's number 1, you can divide this 2, right? The C1 is on the real axis. This is x-axis. So here, z is simply x, right? For the C1 integral, the path is, can you, the path is on this real axis, right? X-axis. So on C1, simply z is x. Because this is x, this is y. So from minus r to r, x squared 1 plus dx plus cr. So I have to draw it again. So let's calculate this is r. On CR, z is r exponential I theta. dz r exponential I theta, I d theta. So this CR integral is half of the circle, so 0 to pi. R exponential I theta, I d theta, r square exponential I 2 theta plus 1. So absolute value of this integral must be smaller than or equal to this. You take the limit, absolute value. Right? Even smaller than this. Right? When denominator is smaller, it's bigger, right? So this must be bigger than with plus 1. Right. So this is 1 over r pi. So the absolute limit of this integral is less than pi over r. So if we take the limit, r goes to infinite, then this goes to 0, right? So after all, so this is a really important step because the integral on the big circle eventually goes to 0 when r becomes very large. That's also the beauty of the complex integral. So maybe I have to do it again. C1, CR, we have I, that's your C. So this whole integral, C, if it goes to R, become infinite. You know already the answer is pi, because of course it's integral theorem. Integral formula. But it becomes limit infinite minus r to r x squared over dx plus cr. And if we know that this goes to 0, right? So this is simply so even though even though you do not know the derivative of octant and x, you still can integrate this function in the complex domain and get the pi. And next time, next week, we are going to have more intriguing complex integrations, but the topic for the quiz is up to today. So I'm thinking about stopping here today. What do you think? Good for your lunch, right? So, buon appetito.